Alright guys, so today we're talking about friction. So we've talked a little bit about this already, but this is just going to go more in depth on what we're talking about with the two different types of friction and how we calculate friction based on the situation that we're dealing with. So, two types of friction. We have kinetic friction. So kinetic friction opposes motion once the object is already in motion. So this is going to be if an object is already moving, so as in this example here, it has a velocity to the right, it's traveling to the right, and friction is going to go to the left and oppose that motion. And that is going to be the kinetic friction because it's moving. If the object is stopped, so it's not moving yet, instead of kinetic friction, it's going to be static friction that is applied in the situation. Static friction is the friction that's applied before something starts moving. Essentially, the molecules in the object and the surface have kind of nested in together, and they don't want to move. They don't want to release and let the object go. So you have to overcome that static friction first before the object will move. Once that object does start moving, however, then it turns into kinetic friction. And static friction has a limit. It will go up until a certain point. But once you pass that point, you overcome that static and it goes to kinetic and it will start moving. If you only apply a little bit of force to something, such as if I have my little pencil case here, I'm applying a little bit of a force to it. It's not moving. It's not going anywhere. But the friction is pushing back against my finger. So I'm trying to push it to the, up, and it's not moving. Friction is pushing back this way to oppose that force. But once I push a little bit more, it pushes back with a little more force. And you can test this yourself by just pushing on any object or pulling on any object. Start by gently pulling on it. You'll feel that the force that it applies to you is going to be equal to the force that you're applying to it until you get to the point where it starts moving. Once I get it moving, it is still going to oppose motion, but it's moving slowly. So it is moving, and it is still pushing back against me, but I overcame that static friction. And once it gets moving, it should require less force to keep it moving than it did to initially get it to start. So again, kinetic opposes motion when it's already in motion. And static friction opposes the initiation of motion. One other note about kinetic friction is that if the kinetic friction and the force that's being applied are equal to each other. So going back to my little pencil case, if I'm pushing on this and friction is equal to the force that I'm applying, it's not going to accelerate. It's going to go at a constant speed. If, however, I'm pushing with more force than friction is applying, then it's going to speed up. It's going to accelerate. But as long as those two forces are equal, as in this example here, there's going to be no acceleration, and we would say that there's no net force. So even though that object is moving, even though there are forces acting on it, those forces equal out. They'll cancel each other out. Therefore, there is no net force. All right, so the next part we're going to talk about is how to actually calculate friction. So again, we talked about there's the two different types of friction. There's kinetic and there's static. So when we're dealing with that in equations, the symbol that we use for friction is this symbol here, and it's called mu. So it's essentially like a U, but with an extra long tail on one side. So, or even an extra tail. So that is mu. It's a Greek letter. And if we're talking about static, we'd put a little s here. If we're talking about kinetic, we would put a little k there. So that differentiates between the two because it depends on if the object is moving or standing still, which of the frictions we're going to use. So with that, we're going to use this equation up here at the top. So this is F equals mu times the normal force. And so remember, with the normal force, that is going to be the opposite of our weight. So we have Fg, which is the force of gravity that pulls down on an object, and that equals the weight. So then the force that opposes that, because the object isn't flying up in the air through space and it's also not being pulled down through the ground, it's staying there, it's stationary. So the normal force is the force of the ground or the surface pushing back up on that object. So when we use this equation, if the object is just on a level surface, then we would say that Fn, the normal force, is equal to the weight, which is the force of gravity. And remember that the other equation that we have is that weight equals the mass times gravity. So remember that weight and mass are different. They're not the same. So, and remember too that weight is a force, and forces are measured in newtons, and mass is measured in kilograms. So if they tell you something is in kilograms, that's talking about mass. If something is in newtons, it's talking about weight. So back to our equation here though. So we have the force of friction equals mu times the normal force. So when we're dealing with this problem, what we need to do is we need to figure out which of the two frictions we're talking about. Are we talking about static friction or are we talking about kinetic friction? So as we talked about earlier, you would do that based on, is the object moving? So a problem might ask you, how much force do you need to apply to get an object moving? If they ask that, we're definitely going to be talking about static friction because that's what's opposing the motion, and we must overcome that force in order for the object to start moving. Versus if they're asking, what is the friction force that's slowing down the object and causing a block that's sliding across a surface to stop? That would be kinetic friction because it's already moving, and that's slowing it down, creating a net force that causes it to decelerate. So with this, back to static. Static friction is always going to be greater than kinetic friction. So if they give you a list of two frictions that are applying on an object, they'll generally label them, but if for whatever reason they didn't, whatever the smaller one is going to be your kinetic, and the larger one is going to be the static, because it always takes more force to get that object moving than it does to keep it moving once it's moving. One note too about the coefficients of friction, which again is what these are, is it will depend on the surface. So we did that experiment a few weeks ago where we tested how much force it required to pull a block on different surfaces. So we tested it on the table, on the floor, on the carpet, on the rug, things like that. And it took more force to move it on certain surfaces. So those surfaces would have had a greater coefficient of friction than surfaces like the table, which is nice and smooth. So the more rough a surface is, the higher the coefficient of friction is going to be. The smoother a surface, the lower coefficient of friction there's going to be. So it's a good thing to keep in mind as you're working with things that will affect the coefficient of friction. One last thing from note standpoint, and then we're going to jump into some practice problems, is so Newton's third law. We've already talked about this, but Newton's third law is for every action, there's an equal and opposite reaction, which essentially is saying if I'm pushing on a surface, it's pushing back on me with the same force that I'm applying to it. We learned in the video that we watched earlier that there is a limit to that. A surface is only able to push back with a certain amount of force based on how strong that object is. So if I'm pushing against this whiteboard, it will eventually break. This is just one of our flimsy whiteboards. It's pretty strong, but if I were to punch it, it would probably break. Versus if you had glass, for instance, glass is going to be stronger probably than this is. But still, if you hit it with something sharp or anything like that, it's probably going to break. So it just depends on the surface, how much force it's allowed to push back with. But ultimately, as much as the object or the surface is capable of pushing back against you with an equal and opposite force, it will do so. We're going to go ahead and start with this practice problem. It's on page 161 of your book. So if you can go ahead and flip to that in your own book, and we'll work through it, and then I'll need you to do something on your own problems based off of this. So you can follow along in your book, or you can just listen to what I'm doing and then try it on your own afterwards. But what the problem says is a 300 kilogram log rests on the ground. Mu s equals 0.74 and mu k equals 0.45. So again, talking about that is the static coefficient of friction and the kinetic coefficient of friction. And you'll note the static one is significantly higher than the kinetic one is. So because as I talked about, it takes more force to get the object moving than it does to keep it moving. What is the frictional force that a pulling truck would have to overcome in order to get the log to move? So we talked about this a minute ago. If it's talking about how much will it have to overcome in order to get something to move, which one are we going to be using? We're going to use static. So because static starts when it's stationary, it's not moving. And that's what it has to be overcome in order to get the object moving. So if we look at the diagram here, they've already drawn it for us, which is helpful. So we have friction pulling back here, opposing motion. We have the applied force here by the truck, and that's what we're solving for. And then because the object is not flying off into space or falling through the ground, we have our normal force and weight that oppose each other there and just cancel each other out. So for this problem, because we are dealing with friction, we will need to figure out that weight so that we can then figure out our normal force. And one note with that, when we put gravity into our equation, because we're dealing with normal force and not weight, we will put it in as positive. So because it's the force that's opposing gravity, which pulls down, but the normal force pulls up. So it's going in a positive direction. So that one will be positive. So yeah, with this, we're going to go ahead and set up an equation, and I'll show you what we're going to do with that.